Welcome back, everyone. It's Mrs. Hanson, and we're continuing work writing out ionic compounds, those types of compounds that are built of ions, a positively charged ion and a negatively charged ion coming together to act as a neutral compound. I had to let my dog in. The compound that we build is known as a formula unit, that basic building block of ionic compounds. I'm introducing common polyatomic ions, and you were given this chart. I'm not asking that you memorize these, but the more you use them, just like with the elemental symbols, the faster you become at locating them and kind of start to hear their names. Let's define a polyatomic ion. You see that prefix poly? Poly, of course, means many. A group of atoms covalently bonded, acting as a single unit, and it carries a charge. These polyatomic ions are groups of atoms all acting as a single ion. There's just more than one type of atom inside this unit, and they end up carrying a charge. Let's get organized and just kind of start looking at these polyatomic ions. Notice that in the first column here, we have a -1 charge. In the next column, these are all polyatomic ions grouped by a -2 charge. And in the far column, I see a few polyatomic ions that are grouped by their -3 charge. I also want to point out that there are a few, not many, but a few that are positively charged. Ammonium and hydronium are just two examples of positive polyatomic ions. Let's focus first on what we said were the -1 family. Notice that we have a formula and the name. H2PO4 -1 charge. We call that dihydrogen phosphate. Next to that, C2H3O2 negative. That name is known as acetate. Dihydrogen phosphate, acetate. Next one down, HSO3 negative is hydrogen sulfite. One more oxygen on that, HSO4 negative, hydrogen sulfate. HCO3 negative, hydrogen carbonate. Can you do me a favor? And I want you to let yourself know that this is also called bicarbonate. Hydrogen carbonate is also called bicarbonate. Anytime you have a hydrogen, for example, hydrogen sulfate could be called bisulfate. Hydrogen sulfite could be called bisulfite. It's just a shorthand way of writing out the element hydrogen in front of that polyatomic ion. So we're just including those in those names. Going back to hearing more polyatomic names, we have nitrite, NO2 -1. Notice we add one more oxygen, NO3 -1, and it becomes nitrate. Cyanide. I'm going to color this one green. Cyanide, hydroxide. I'm coloring them green because I'm hearing different endings, and we're going to focus those really careful. Notice those are "ide," cyanide, hydroxide. But otherwise, I've been hearing "ite" and "ate." Permanganate, MnO4 negative. Hypochlorite, ClO -1. Chlorite, chlorate, perchlorate, all different by the number of oxygens present in that formula. Hypochlorite, ClO negative. Chlorite, ClO2 negative. Chlorate, ClO3 negative. And then perchlorate has 4 oxygens, ClO4, all with a -1 charge. We move over then to the -2s, and I hear hydrogen phosphate, oxalate, sulfite, sulfate, carbonate, chromate, dichromate, silicate. And then over here again, phosphite, phosphate, And those positive polyatomics, ammonium, NH4 with a +1 charge, and hydronium, we'll learn that's the acid ion. Hydronium is H3O +1. So we just spent time hearing the names, and hearing the names is the first step in kind of being able to recognize, recognition there of polyatomic ions. Do you hear the endings ite and ate and ite for the most common endings of the polyatomic ion chart? I'm hearing over and over phosphate, acetate, here's sulfite, sulfate, nitrite, nitrate. Ate or ite endings are the most common endings for polyatomic ions. Notice that these are mostly oxy ions. Oxyanions. It means that it has a first letter, like the first elemental symbol. Sorry, my hand hit that. And then oxygens attached. So for instance, notice phosphite. The element phosphorus is the root name. And then of course the number of oxygens. Phosphite, phosphate. That's an oxyanion. Sulfite, sulfate. It's oxygen on the sulfur. Carbonate has oxygens on the carbon, and so forth. So we see a lot of oxygens in these polyatomic ions. I do see some exceptions to the ite endings. As I modeled, there are two in the -1 column. Cyanide, it's a polyatomic ion built of carbon and nitrogen bonded together, carrying an overall net -1 charge. Underneath that is the base ion called hydroxide, a polyatomic ion bonded of O and H with a net -1 charge. And here I could see that we have ammonium. Ammonium is a polyatomic ion built of a central atom nitrogen chemically bonded to 4 hydrogens, all carrying a +1 charge. A group of atoms acting as a unit carrying a positive charge. The other is hydronium. This is H3O +1. So H3O, it's an oxygen bonded to 3 hydrogens, all carrying a net positive charge known as hydronium. So polyatomic ions have covalent bonds holding them together. For instance, we have, let's just say sulfite. If I have all of those oxygens bound together and I just have all of these electron dots filled in, and I know that overall it will carry a -2 charge. Within the polyatomic ion, there are covalent bonds holding all of these nonmetals together. But I can take this net negative and actually put it next to a positive ion to create an ionic compound we commonly call salts. So as we do that in the next step, our job was just to get familiar with naming and hearing some of these formulas. So let's spend a moment of investigating your polyatomic ion chart and just go to work, pause the video, use your chart, and just write the formulas for each of these examples. Use your polyatomic chart and complete the names. Come back to me when ready. All right, you're ready then. Let's begin. Ammonium chemical formula is NH4 and the charge is a +1. There's 1 nitrogen chemically bonded to 4 hydrogens with a net +1 charge. Sulfate, you found that. It's SO4, 1 sulfur chemically bonded to 4 oxygens carrying a net -2 charge. Sulfate. 1 less oxygen and we find sulfite. That sulfur is chemically bonded to just 3 oxygens, still carrying a -2 charge. Right there is carbonate. That's carbon chemically bonded to 3 oxygens, carrying a net -2 charge. Carbonate. When you found nitrate, That's a nitrogen chemically bonded to 3 oxygens with a net -1 charge. Permanganate, we say that, permanganate. That has the element manganese in it, MnO4 with a net -1 charge. Hypochlorite, hypo, that's HClO. Those are chlorines, ClO -1. Phosphate, that has a phosphorus chemically bonded to 4 oxygens with a net -3 charge. Cyanide, cyanide, Cn -1. A carbon bonded to nitrogen with a net -1 overall charge. And under that is hydroxide. O bonded to an H with a net -1 charge, hydroxide. And the purpose there really was just to get you looking and saying names of polyatomic ions. I wanted to emphasize what I call a family of ions and how they're related by name and oxygens. Hypochlorite, I was writing a hydrogen for hypo, my bad. ClO -1. 1 oxygen chemically bonded to a chlorine. Hypo means below. If I take off the prefix hypo and just go to plain old chlorite, I then go up 1 more oxygen, right? Hypo means 1 below, so I remove an oxygen. I still keep the charge the same, chlorite, ClO2 -1. When ite changes to 8, we add 1 more oxygen. That's 1 chlorine chemically bonded to 3 oxygen atoms with a net -1 charge. And per, sometimes you hear that prefix hyper, means above. We add 1 more oxygen and we get perchlorate, ClO4 -1. So you can see changing the oxygen on that main element of chlorine determines the name. So you really want to use your polyatomic ion chart to find the root word and then determine how many oxygens are on there. So changing the oxygen changes the name of the polyatomic ion, just as we represented with that example. When we write ternary ionic compounds, I want to say that these are 3 elements in a compound, but I still want to emphasize they're just still 2 ions. It's just that one of them is going to be a polyatomic ion. So that's why we have more than one. Usually there's oxygen in the polyatomic ion, more than one different type of element. But one with a polyatomic, or it could be both polyatomics. 2 polyatomic ions could hook together if one's positive and one's negative. And that's really the first rule, is we always write the positive first and consider its charge. We write the negative ion last, always, and consider its charge. We use the crisscross method to find an electrically neutral compound. That's going to help us find our subscripts. And if we need to take more than 1 polyatomic ion to balance those charges, we place it inside of a parenthesis. Never change the subscripts on a polyatomic ion. Instead, I want you to plunk it inside of a parenthesis and place its subscript outside the parenthesis. Do not change those polyatomic ions. So let's say, for example, I wanted to write a chemical formula for a compound named sodium nitrite. I want you to hear the ITE ending very carefully, because that ITE, that's your clue that it's a polyatomic ion. Polyatomic ions end in ite or ate. Binary ions end in ide. Remember that from our previous lesson. So let's just take a peek here at how we're doing that. Sodium on our periodic table, we know, is in group 1A, and so sodium carries a +1 charge. From our polyatomic ion chart is going to show us nitrite carries a -1 charge. and I was just looking for that chart. Did I delete it? What happened? Here it is, nitrite. And so here all of a sudden I can see right here is nitrite. Again, the more you use your chart, the more familiar you become. So nitrite, that is NO2 minus 1. Sodium, Na plus 1. Notice how a plus 1 and a minus 1 electrically balance to 0. It's like having a sodium ion with a magnitude of plus 1, and 1 unit of NO2 in its magnitude is minus 1. 1 unit of a plus with 1 unit of a negative chemically balanced to be 0. Sodium nitrite is simply written NaNO2. It is considered to be a ternary ionic compound because there are 3 different elements. I see a sodium, Na, I see a nitrogen, elemental symbol N, and I see an oxygen. I see 2 oxygens, elemental symbol O. 3 different elements, but no matter what, there's still just 2 ions. There is a sodium ion, and there is a nitrite ion. Na is a plus 1, NO2, negative 1. 2 ions chemically bonded together. And you can see another example here. Here's barium sulfate. Notice the barium ion carries a plus 2 charge. We know that because barium lives in group 2A in the heartland of fixed charge of a plus 2. So Ba is a plus 2. And we're hooking it to a sulfate, SO4, my screen keeps jumping, SO4 minus 2. And so here, sulfate. Now where did I find that? You're right. Sulfate came from right here on our polyatomic ion chart. I knew that because I could hear the 8 ending. ATE lets us know it's a polyatomic ion. Notice that a plus 2 and a minus 2 is already chemically balanced. Barium sulfate. Just say the names of the 2 ions. Barium does not require a Roman numeral. It's in the heartland of I know you're a plus 2 charge. Finally, we have an example of magnesium with a magnitude of plus 2 and hydroxide. So think about what that means visually. Magnesium is 2 positives big, but the polyatomic ion of hydroxide only carries a minus 1. So 1 unit of a minus 1 and 2, we get a 1 unit of a plus 2, 1 unit of a minus 1. We can clearly see that it's not yet balanced electrically. We're going to need a second polyatomic ion to balance the charge. Now the trick here says, here's magnesium, it's plus 2. Here's hydroxide, it's a minus 1. We're going to crisscross just as we did before, and we'll bring those around and down. Now I want to take 2 whole groups of hydroxide. So inside of a parenthesis, OH taken twice. We read that by saying magnesium hydroxide. And we would say Mg, and then you say OH, and then you would say taken twice to represent that there's a subscript of 2 outside the parenthesis. Now let's kind of emphasize why that's important. What's the difference between MgOH2 and MgOH taken twice? If I forget the parenthesis, the subscript 2 only communicates to the hydrogen. I want to take 2 groups of hydroxide, and that's the importance of the parenthesis. And so anytime we're taking more than 1 polyatomic ion, we place it inside of a parenthesis and put its subscript outside. Never change the polyatomic ion subscripts. It is not okay to double both. That's not good. And we want to make sure that we don't just talk to the last element, place it inside of the parenthesis. So let's practice many practices. All right, got my tool pages, periodic table, polyatomic ion chart. Those are the tools I need to write any formula for an ionic compound. Let's write the formula for the following compounds. They're going to be composed of cations, which are positive, and anions, which are negative. First one reads sodium, and we'll hook it to bicarbonate. Sodium lives in the first family. We know that that's a fixed charge, and so therefore any element in the first column will carry a +1 charge. I'm going to write the elemental symbol Na and its charge up high. Bicarbonate. Here the 8, that tells us it's polyatomic. Bicarbonate. Now, a moment ago I said bicarbonate is another way of saying the word hydrogen. So we want to find hydrogen carbonate. That's right here, HCO3 -1. We made a note a moment ago that that's also called bicarbonate. So we have HCO3, all part of the formula for bicarbonate, or also called hydrogen carbonate. Hey, look, a +1 and a balanced -1. We're already electrically neutral. +1s and -1s cancel each other out. So my chemical formula simply becomes NaHCO3, sodium bicarbonate. That's baking soda. Letter B gives me potassium, which is K, which is right under sodium. So we could see it will also be a +1. And a polyatomic ion. Here the 8 ending. That's my clue that I know it's polyatomic. 8 ite endings. It's called nitrate. With the polyatomic ion, I can find nitrate, NO3, and it carries a -1. Hey, look, that's already electrically balanced. A +1 neutralizes a -1. So letter B, all cleaned up, KNO3, and that's red potassium nitrate. Letter C gives us 2 polyatomics. You hear this one? Ammonium. We're learning that that's a positive polyatomic ion, that it's NH4, 1 nitrogen chemically bonded to 4 hydrogens, and it carries a +1 charge. We're going to chemically bond that to sulfate. Sulfate, polyatomic, here the 8 ending, that sulfate is SO4 -2. Here we go. A +1 and a -2 is not yet chemically balanced. Think of it as 1 charge on NH4 and a second ion that has a magnitude of -2. The sulfur is bonded to 4 oxygens and it's a -2 charge overall. I should have included that in. 1 unit of a -2. Now I can see that 1 unit of a +1 needs a second helper. 2 units of a +1 will balance the charge of a -2. So remember how we do that? We bring this around and down. We need to place NH4 inside of a parenthesis and show that we need 2 of them to electrically balance the sulfate at a -2 charge. 2 units of an NH4 electrically balance 1 unit of an SO4. We do not need the parenthesis taken 1 time. We don't need that. We're just going to say NH4 taken twice, SO4. That is ammonium sulfate. On to letter D. Magnesium phosphate. So here we're finding magnesium in the heartland of the +2 fixed charge. And it's going to chemically bond to phosphate. Hear the ATE ending, phosphate. That's my polyatomic ion clue. There's one phosphorus chemically bonded to 4 oxygens, and it carries a -3 charge, a group of atoms acting as a unit carrying a net charge of 3 negatives. All right, so here we have an opportunity to think about crisscrossing charge. That 3 comes around and down and tells me how many magnesium ions we need. The 2 will come around and down and tell me how many phosphate ions we need. When I want to take more than 1 magnesium, I simply place that 3 next to its symbol. But when I need to take more than 1 polyatomic ion, I place it inside a parentheses and its subscript outside. We say Mg3PO4 taken twice. Magnesium is a +2 charge. We can see that it's going to require 3 positive 2s to balance 2 polyatomic ions that carry a -3 charge. Do you see with that visual that my net is a +6 and the net for the negative is a -6? We have indeed balanced electrically. I have PO4 taken twice. 2 of those -3s electrically balance 3 units of Mg, each at a +2. All right, we'll keep going. Practice, practice. We have calcium hooking to bisulfate. This is letter E. So calcium, who lives right here in group 2A, do you see calcium? Telling me that it's going to lose 2 electrons. Calcium is going to develop a +2 charge. All of these in the second column are always +2s. I see bisulfate. Remember, the term bi represents hydrogen in the polyatomic ion chart. So we're looking for hydrogen sulfate, ATE ending. Hydrogen sulfate or bisulfate. HSO4, all bonded in one big unit, resulting in a -1 net negative charge. Around and down, the calcium's charge becomes the subscript on hydrogen sulfate. The -1 becomes the subscript on the calcium. When we need to take more than 1 polyatomic ion, it gets placed inside of a parenthesis and the subscript outside. So cleaning that up, we say Ca, parenthesis, HSO4 taken twice. That's calcium bisulfate. You may also say calcium hydrogen sulfate. And we have one more in this unit. It's barium and hydroxide. Now, barium is an element found in group 2A. Therefore, I know it will form a +2 charge when it loses its 2 electrons. Hydroxide, right here, the polyatomic ion hydroxide is OH, and it carries a net -1, an oxygen bonded to a hydrogen with a net -1. We need to do our crisscross. The 2 tells me how many groups of hydroxide. Inside of a parenthesis, I want to take 2 groups of OH, and I need 1 barium. So we'll write that as BaOH taken twice. Let me emphasize, let's just use sodium chloride, sodium chlorite, sodium chlorate, just to hear the endings. Ide, ite, ate. Sodium is Na, and it carries a +1 charge. So that I know just from where it lives, sodium is a +1 charge. When I hear chloride, it's a monatomic ion, Cl negative, chloride. When I hear ite in 8, chlorite, chlorate. But remember, from the periodic table, we hear ide, fluoride, chloride, bromide, iodide. Ide says go to the periodic table and find the negative element. Ite and 8, those endings tell us go to the polyatomic ion chart. So NaCl, sodium chloride. Sodium chlorite. Na is a plus, chlorite is a polyatomic ion, which has 2 oxygens in terms of its formula. NaClO2, sodium chlorite. And then sodium chlorate, NaClO3. All of these are built with +1 plus sodium ions, and the negative chloride, chlorate, chlorite. Let's try some more. Instead of building, let's now name. All right, so I'm going to name these. Here I see the first elemental symbol, Na. So I find the positive ion on the periodic table. Na represents the element sodium. Does sodium need a Roman numeral? And the answer is no, because it is a fixed charge. So no Roman numeral necessary. Even though I see lots of different elements, I have just 2 ions. I have a sodium +1 and a carbonate -2. Do you see carbonate? Right here is the unit of CO3, sodium carbonate. I found the symbol sodium, Na, and named it. Check to see if it needed a Roman numeral. It does not. Then the last ion is a group of atoms acting as a unit. More than one atom are present in that last part of the formula. So that's how I know to go to the polyatomic chart. CO3 will be called carbonate. Letter B, the element Ca stands for the element calcium. So the symbol Ca is calcium. It does not need a Roman numeral because it has a fixed charge of +2. Here's a group of atoms acting as a unit. Groups of atoms are called polyatomics. OH is a polyatomic called hydroxide. So here I call this calcium hydroxide. Letter C, I see the elemental symbol Mg. On my periodic table, I see that's the element magnesium. Magnesium is a fixed charge of +2, so no Roman numeral. It's bonded to a group of atoms acting as a unit, NO3. And when I find NO3, I can see its name is nitrate. This is called magnesium nitrate. Mn is the element manganese. Now manganese lives right in the heartland of, I don't know your charge by where you live. It's a variable charge. That tells me it must have a Roman numeral as part of its name. I now see a polyatomic ion, CH3CO2. Now that is just reorganized as acetate. C2H3O2 negative is one way that you see the polyatomic ion called acetate. If I wanted to tell you how they're bonded together, I could show you CH3CO2, each with the -1. Just realize that those are the same formulas, they're just written in a different order. There are 2 carbons, 3 hydrogens, and 2 oxygens in the polyatomic ion called acetate. Acetate is a -1 charge. You see that? So I have 2 groups of a -1. C2H3O2 is a group of atoms acting as a unit carrying a -1 charge. 2 groups of them, each at a -1. What must the charge be on the manganese so that it equalizes to 0? Well, you're right. You're going to uncriss-cross, right? This has to be a +2 charge. Manganese +2 will neutralize the 2 units of a -1. Manganese 2 acetate. With its +2 charge, it neutralized the 2 groupings of the -1 acetate. Let's go on to letter E. I'm going to erase to give myself room. Letter E says we have FeHSO3 taken 3 times. A group of atoms acting as a unit carrying a charge. Well, Fe is the element iron. And again, iron lives in the heartland of, I have to tell you its charge with the Roman numeral. It has a variable charge. I'm going to leave a parenthesis. HSO3 is known as hydrogen sulfite, or you could call it bisulfite. Either one is absolutely fine. Whoops, bisulfite. That's correct. So I'll just write it this way this time. Hydrogen sulfite. And then I'll also let you know that it's perfectly okay to call it bisulfite. What's missing is the charge on the ion. So hydrogen sulfite is a -1 charge, and there's 3 of them there. It's like writing HSO3 -1 3 times. Each one of those represents a -1 charge. So 3 individual units of -1. We have 1 iron that's responsible for neutralizing all 3 of those -1 charge. Clearly you see that its magnitude must be a +3 so that it balances 3 units of a -1. That 3 outside the parenthesis came from the iron's +3 charge. This is called iron 3 hydrogen sulfite or iron 3 bisulfite. And one more in our group, letter F. This has the element Mg, already highlighted. Mg stands for the element magnesium. Now magnesium does not need a Roman numeral because we know its charge is always a +2. So no Roman numeral. We just go name the last name here, PO4. A group of atoms acting as a unit, so I know to find its polyatomic ion name. Magnesium phosphate. 2 separate words. It looks like I crammed them together. Magnesium phosphate. You can see here, magnesium, this 2, that told me it was a +2. This 3 told me phosphate was a -3, so we're just kind of uncriss-crossing to work out charges. But I don't have to say the charge with magnesium like I did with those transition elements. For letter F, we simply say magnesium phosphate. Excellent work. Name each ionic compound. Name each ionic compound. Repetition is our friend. Pause the video, work ahead. I want you to just kind of finish all of these so that when you come back to the video, you're simply checking with me. Working ahead. All right, letter A. NH4 plus is ammonium. Cl negative, chloride. This is called ammonium chloride. Letter B. Pb stands for lead. Lead requires a Roman numeral. It is not a fixed charge, it's a variable charge. Sulfate. You found a group of atoms acting as a unit carrying a charge. Last name, sulfate. If sulfate is a -2, you now know lead must be a +2 to electrically balance. A +2 and a -2 equals 0. Lead 2 sulfate. Cu stands for the element copper. You know copper requires a Roman numeral. It's a variable charge. I'll leave a parenthesis. NO3, that's a group of atoms acting as a unit. You found it to be nitrate. That's its last name. Nitrate is a -1. Two groups of a -1 is chemically or electrically balanced with a +2 copper. Copper with a +2 will electrically balance two groups of a -1. That's how I'm reading that. Cu1, NO3 taken twice to create an electrically balanced compound. One copper at a +2 electrically balances two groups of a -1. Remember, the Roman numeral is the charge, not how many you have. Letter D is calcium. Ca, the element calcium. It's a fixed charge of +2. HCO3, that's a polyatomic ion, a group of atoms acting as a unit, carrying a charge. I'll name that bicarbonate. You could call that hydrogen carbonate. No Roman numeral because of fixed charge on calcium. But letter E, elemental iron, is a variable charge, so I'll leave space. NO3 again, that's learning very quickly, that's called nitrate. There are two groups of nitrate. Each one carries a -1 charge, right? That's how I'm reading that. NO3 taken twice. NO3 we can see carries a -1. What charge might the iron have to balance that? You're right, it was a +2 charge. This 2 came from the iron. The 1, it's not there, but we know it's there, came from the nitrate. Iron 2 nitrate. Letter A on the next set has two polyatomic ions. The first is the positive, called ammonium. The last name comes from right here, SO4. We're learning to call that sulfate. That compound is named ammonium sulfate. Here's the first element in letter B. Elemental symbol Na stands for sodium. Here is a whole lot of elements. It's a group of elements acting as a unit, carrying a charge. H2PO4 negative. That's right there on our chart. It's called dihydrogen phosphate. All that has to be written out. Element Cr represents chromium. Remember, that's a variable charge. So we do need a Roman numeral for chromium. I'm going to put a parenthesis and leave some space. Chromium. And then CH3CO2 negative. We called that acetate. Remember that you can write that CH3CO2 negative as well. So that's acetate. The 3 outside the acetate told me chromium was a +3. So 1, 2, 3. We had C2H3O2. That's another way to write this. C2H3O2. 2 carbons, 3 H's, and 2 O's. There's 3 groups of those. See how I have 3 separate -1 ions? That's what this 3 is telling me. There's 3 of them there. I only have 1 chromium. It must have a magnitude of charge of +3 to electrically balance 3 units of a -1. Chromium 3 acetate. Let's keep going. Letter D, Sn stands for the element tin. Tin is a variable charge. I'm going to leave some space for my Roman numeral. HPO4 is a -2 charge. So I'm going to write it as hydrogen phosphate. Now think of what that means. I need some room here, so I'm going to just erase these answers so I can draw in that space. All right, so here I have HPO4, and it is a -2 charge. 1, 2. And there's 2 of them in that formula. That's what the parenthesis taken twice. 2 units of HPO4, each of those is a magnitude of charge of -2. What must the charge on the tin be so that it's electrically neutralizing the net -4 I'm seeing? Well, you're right. 1 +4 is going to neutralize 2 groups of -2. This is tin 4 hydrogen phosphate. I hope you got that one. The last one is the elemental symbol for nickel, and nickel is also a variable charge, so I'm going to leave a parenthesis space. PO4, we're learning, represents the polyatomic ion called phosphate. Now we have to determine what the charge is on nickel. Well, let's see. Phosphate is a -3 charge. And again, I'm going to need just some room. So I'm going to put this as a visual. So here I have PO4, and I have 3 negatives. PO4, 3 negatives. So 2 groups of a -3 charge each. So right now I'm at a -6. I know that I need a +6 all together to be electrically neutral. What must the nickel be so that when I take 3 of them, I end up with an equalized charge? Well, you're right. I'm going to need nickel to be a +2 charge so that by the time I'm done writing 3 of them, I've neutralized the -6 overall from phosphate. Remember, just uncriss-cross here. So the 3 came from phosphate's -3. This 2 came from nickel's +2. This is nickel 2 phosphate. Whew, we're doing good work. Write the formula for each name. Now, if you've not tried these out, take your time, stop the video, then come back, because I'm simply going to write formulas and names as needed. Magnesium carbonate. Mg is a +2. Carbonate, CO3 -2. This turns into MgCO3, electrically neutral. Letter B required a Roman numeral, so I said use a Roman numeral 1. Nickel 1 sulfate. Nickel with a +1. Sulfate, SO4, it's a -2. So I write that Ni2SO4. Nickel 1 sulfate, Ni2SO4. We crisscrossed. The 2 became the subscript for the nickel. And I only need 1 group of sulfate, so no parenthesis needed. Copper, +2. Hydroxide, -1. CuOH, taken twice. Letter D. Potassium, +1. Hydrogen phosphate, HPO4, -2. You see that, right? Hydrogen phosphate, HPO4, -2. And so I crisscross and we get K2HPO4. Gold with a +3. Nitrate with a -1. AuNO3 taken 3 times. Lithium phosphate. Li is a +1. Phosphate is a -3. Li3PO4, lithium phosphate. Letter G, aluminum, +3. Bicarbonate, HCO3, -1. Crisscross, in a parenthesis, Al, HCO3, taken 3 times. Chromos is the low charge. This would be called chromium 1 cyanide. Chromium with a +1 charge. Cyanide, Cn -1. We're balanced. Cr, Cn. Copper 1, sulfite. Copper with its +1, sulfite with its -2, we crisscross. Cu2SO3. Aluminum nitrate. Al to +3, nitrate to -1. We need 3 groups of that -1, so we read that AlNO3 taken 3 times. Tin 2 acetate. Tin +2, acetate with a -1, Sn parentheses C2H3O2 taken twice. It is absolutely all right to see acetate written as this as well. So I'll show them both ways. Sn CH3CO2 taken twice. Lead 4, lead with a +4, carbonate with a -2. When you crisscross, we would get Pb2CO3 taken 4 times. But that would get marked wrong because we can reduce that ratio, and if you can, you need to. So Pb parentheses CO3 taken twice. We want the 1:2 ratio instead of the 2:4 ratio. Lowest ratio possible. That was letter D. How about E? Zinc. That one we know is always a +2, so that's a fixed charge, no Roman numeral necessary. Hydrogen phosphate was also a -2, so that's electrically balanced. ZnHPO4, all one formula. Manganese needs a Roman numeral. Let's tell you it's manganese 2. That one was tough without the Roman numeral, manganese 2. And then dihydrogen phosphate, H2PO4, that carries a -1 charge. Mn, a +2, in a parenthesis, take that polyatomic ion, taken twice. Oh my goodness, home stretch, we can do this. Letter G, ammonium, polyatomic ion, NH4, carries a +1 charge. Cyanide, polyatomic ion as well, carries a -1. That's electrically neutral as written, NH4Cn. And one more to check. Iron, Fe, it carries a +2 based on that Roman numeral. And nitrate, -1. Fe, parenthesis, KNO3, taken twice. We've been working really hard on ionic compounds. These ionic compounds, we've been practicing binary ionic, ternary ionic, naming and writing formulas, and the drill work is so important because practice makes permanent. Practice builds proficiency, and most importantly for quiz day, practice, practice, practice builds speed, and you have to be able to do these quickly to finish in time. So keep practicing, my friends. These ionic compounds are commonly called salts. We know that these are always solids at room temperature. They have extremely high melting points and boiling points. That when ionic compounds we call salts dissolve in water, they separate into their respective ions. They separate into their positive cations and negative anions. When we see these positives and negatives in a water solution, we will learn to call those ions electrolytes because they will be able to conduct an electric current when dissolved in water. You've concluded your Chapter 3 work and on to your homework practices. Keep going. Work to memorize those polyatomic ions, even though you'll be provided a chart. But the more you say them, the more you get familiar, the more proficient you become.